right, gas laws. Remember that you typically measure gases in terms of volume, temperature, and pressure. And these laws are based on the kinetic molecular theory of gases, which is on page 9 of your textbook. And we touched on a few of those concepts in our foldable for states of matter. So temperature, when you're dealing with the gas laws, temperature has to be in Kelvin. And to convert Celsius to Kelvin, you just have to add 273. That is not something that's in your data booklet, but should be easy to remember. Pressure, the SI unit is a Pascal. Sometimes you'll see it in bars, measured in the unit of bars, specifically if it's talking about the weather and hurricanes. 1 bar is 10 to the 5th pascals, and that is close to 1 atm. So there's different units of pressure that you have to know about. For IB purposes, we tend to talk about Pascal or kilopascals. And so something to remember is that 1 atm is equal to 101.3 kilopascals. But we typically just deal in pascals. Now, Boyle's, Charles, and Gay-Lussac are our 3 different individual laws that compare pressure and volume, or temperature and volume, or pressure and temperature. We can put all 3 of those together and we can get our combined gas law. Again, this is not given to you in your data booklet, but it's for going from one set of conditions to another set of conditions. If there was no change in temperature, then you would just take out temperature and you would be left with Boyle's law, V1P1 equals V2P2. The ideal gas law is when you're trying to put in there the amount of gas or the moles of gas. And so we have PV equals nRT. That is given to you in your data booklet in section 1. R is also given to you. R is also given to you in your data booklet. 8.31 joules per Kelvin mole. In Chem 1, we used the constant R equals 0.0821 liter ATM over mole Kelvin, but IB we tend to use this value instead. A joule, the letter J there, remember, is the unit for energy. That's equal to 1 Pascal times meters cubed. So your unit for pressure should be in a Pascal, and then the unit for volume should be in meters cubed. One variation of the ideal gas law is PM equals DRT, or in the PM you are dirty. So the M stands for the molar mass of the substance, and D stands for the density. And remember, density is mass over volume. So you have lots of different options on how to solve different gas laws. The hardest part about this is knowing which law to use, and you figure that out based on what you're given and what you're looking for. All right, so for example, we have a molar mass of a gas at STP. So if we're at STP, then we know the temperature is 0 Celsius or 273 Kelvin, and our pressure is going to be 100 pascals, and then we're calculating the molar volume at 25 degrees Celsius and the same pressure. So pressure is not changing, so we really don't care about that. We have volume and temperature. We're changing it to a second temperature, and so we want to know what the second volume is going to be. So we have a set of conditions that we're changing. So we're going to use the combined gas law. V1P1 equals V2P2, and that is over T1 and T2. Since the pressure is held constant, it's not changing, we can simply remove the pressure and we get our formula that we're going to be using. V1 over T1 equals V2 over T2. Remember though that temperature has to be in Kelvin when you do gas laws. So we're going to have to take our 25 degrees Celsius. So T2 is 25 degrees Celsius plus 273 makes that 298 Kelvin. And then we can simply plug in and solve for V2. Solve for V2. You can do this before you put in the values, multiply both sides by T2, and the T2s will cancel out. So to solve for V2, we would do V1 times T2 divided by T1. If you'd rather put in your values and then solve for the missing variable, we can do it that way as well. So the initial volume, or V1, would be 22.7 decimeters cubed, and the initial temperature, 273 Kelvin, is equal to V2, which is what we're solving for, divided by 298 Kelvin. So we would multiply both sides by 298 to get rid of the temperature. So X would then equal 298 times 22.7 divided by 273. We want to go back to the numbers that were given to us in the problem, and we have three significant figures. The temperature is also three significant figures because we've converted it to Kelvin. So the answer would be 24.8. Kelvin cancels, leaving decimeters cubed for the unit. All right, looking at the next problem. We have helium party balloon, so we know what the element is, or the gas. We have a volume of 18.0 decimeters cubed. We have a temperature. We have a pressure given to us in kilopascals. And we want to calculate the mass of helium. So we don't have a formula that gives us mass, but we do have a formula that will give us moles. And then we can convert to mass. So if we use the ideal gas law, PV equals nRT, or PIV-NRT, we can solve for moles and then convert from moles to grams. We just have to make sure everything is in the correct unit. So volume needs to be in meters cubed. And so to go from decimeter to meter, we would go one place to the left, but it's being cubed, so we're going to do that 3 times. And so the volume is 0.0180 meters cubed. Temperature needs to be in Kelvin, so we would say 25 plus 273, and we would get 298 Kelvin. Pressure needs to be in pascals, so to go from kilopascals to pascals, if you're using King Henry, K to U, so that's 3 places to the right, so we would have 180,000 pascals. So then we can plug it in and solve for our missing variable. If you wanted to do it prior to plugging numbers in before it gets too confusing, you can divide by RT on both sides to get N by itself. So we have the pressure times the volume divided by, remember R is the gas law constant, 8.31 joules per Kelvin mole. And then that's going to multiply by the temperature. Make sure that when you type it into the calculator, you use your parentheses so that it is multiplying before it divides. And then our Pascal meter cubed will cancel our joule. Kelvin and Kelvin cancel, and we're left with mole. Looking back at the numbers they give us, we're going to use 3 significant figures, so 0.785 moles of helium. Now the question says calculate the mass, so we're not quite done. Now we need to convert from moles to grams, so we bring moles to the bottom, grams on the top, and then we can look at the periodic table, and we see that 1 mole of helium has a molar mass of 4.00. And so we're going to take our moles and multiply by 4, divide by 1, and we get 3.14 grams of helium. All right, let's look at one more example. So it says a gas has a density, grams per decimeters cubed, so that's our density. We have a temperature of 27, and because this is a gas, we're going to need that to be in Kelvin, so we add 273 and we get 300 Kelvin. And then we have a pressure that we would need in pascals, so we're going to move the decimal 3 places to the right, so 92,000 pascals, and we want to know what the molar mass is. So here we have a situation that we're going to use the application of the ideal gas law, or in the PM, you are dir T, PM equals dRT, and we're solving for the molar mass, which is the M. So we're going to divide both sides by P, and so the molar mass is equal to density times the gas law constant times temperature divided by pressure. And so we would set that up. The density, 1.65 grams per decimeters cubed, times R, which is 8.31 joules per Kelvin mole, times our temperature, 300 Kelvin. Now, because the density is in decimeters cubed, we can actually use the kilopascal version of pressure instead of converting it to pascals, or you could have converted this to meters cubed and then use pascals. So either use decimeters cubed and kilopascals, or you need to be using meters cubed and pascal. So I'm going to divide that by 92 kilopascals. That way the decimeters cubed and the kilopascals would cancel the joule, and Kelvin cancels Kelvin, and then we have grams per mole, which is the unit for molar mass. So we will plug that into the calculator. Based on the numbers given to us, we want 3 for our significant figures. So we have an answer of 44.7 grams per mole. Now, if they gave us a list of gases to choose from, we could use the molar mass to identify the gas, but because they did not do that for us, we have no way of determining what the type of gas is. All right, so those gas laws are for ideal gases. When we talk about real gases, we have to remember that real gases deviate from ideal behavior because gases have intermolecular forces. They're just weak. So gases are most ideal at low pressure and high temperature. So when we get to high pressure or low temperature, that's when there's more deviation. Van der Waals is an equation that we can use to correct for that. And it's this formula right here. However, at the SL level, we don't need to actually use that formula. If you were taking HL or AP chemistry, then you would need to be able to convert with that or use that formula for finding the real gas variables. Again, low pressure, high temperature is the most ideal, and then when you are at high pressure or low temperature, then you're going to deviate the most from being ideal. Don't forget to fill out the Google form and make sure that you try those practice problems.